We have spent the last decade building pipeline that moves data. But in era of software 3.0, moving data isn't enough. If your pipeline breaks today, a human has to fix it. Adds a bottleneck and it cannot scale. The next generation of data engineering isn't about writing code better. It's about building an agentic architecture that evolves itself. Hi, I'm Nila Parikh. This is 7-part roadmap building a data engineer 3.0. Let's define a failure points before we start with a hands-on lab. Operational input is frequently integrated through inconsistencies like drifting, formats, and duplicate, eventually break our system. Poor data quality causing losses exceeding up to 5 million in every 1 to 4 organization and could up to 500 million for many blue chips. So what could be a solution? One is certainly software 3.0. But let's understand what is software 3.0. It's a quite vague term as of today. However, let me metaphorically explain in our own context. Think of like a cavity wall. Two rigid layers of brick with the wriggling middle space which is hollow. And that's where we handle this mess. The AI lives in that middle gap, absorbing the vibration and variations of messy data, expanding or contracting to fix the discrepancies, while the outer brick remain immovable, providing much needed enforcement and structural integrity. Moving from a static code to programmable operators where we use agents to find likely repairs in seconds. Now let's just see this same thing what we discussed in a live example. So let's go on Visual Studio Code. In this hands-on, we will cover 3 important things. First, how to configure and run. The second, end-to-end run. And third, get overall familiarization with this example. In this particular lesson, we won't deep dive into individual component. For that, we have another 6 lessons coming after this. This first lesson will set a good stepping stone to understand the project end to end. And that will help whenever we are deep diving into it, we will have the broader and larger context, why we are doing and what are the benefits of doing in such a way. The very first thing to start is always a README file. README file will let you have quick commands, the documentation map. It's well documented and it has all the lesson clearly defined with the exercises that you can benefit from. The README will also take you to some other important documentation such as architecture, data, and operations and test coverage. All the commands are documented under the runbook. Reset and recovery will help you to bring the project back to the original state. That means you can do you can actually go on this project couple of times, and if you think that, oh yeah, we have moved a little bit far and we need to come back, you can always reset the project. And also setup and verify will ensure that you have a clean setup that require. Most probably everyone would need just a single command to set up the project unless you want to go and install the project in a specific configuration. All you need to do is pip install dot. That will install all the dependencies and everything it need. The second thing is you can just run the status command. Then after the status command will read all the config and tell you what it finds. Then you can validate if everything that you want is as per the status or not. Environment.example is a place which you can copy as an N file and just replace with your own configuration. It will be picked up by the status itself. And then finally, verify. Verify will ensure that your project state is in correct state to run all these examples. So that's it. That's a perfect state. Now, once we can actually run the loop command. Loop command is the one that make us run everything end to end. And I'm running with a maximum 2 iterations. That means it will stop after 2 iterations. But let's understand what it does. We got a input files where we have a discrepancies and the data inconsistencies. So this input files has been read. The gold standard is something which is used for compare. It does nothing much more. But from here, we read them, we process them. Some of them will be processed deterministically. Some of them will be processed non-deterministically. It will process everything that deterministically put into master. What it can't process deterministically, it processes in a failure and then attempt to process them in a success. But instead of that, there is a better way, the dashboard, which is running on a Streamlit app. And once this process is complete, we'll walk through there. Perfect. The dashboard is there. So now just refresh it. So we get the last. Go to the round robins. And you can see here all the information is needed. Now, this recall what we discussed about software 3.0. It tells you the execution and the judge metrics. It's a more advanced when we discuss the judge. It will help us to understand what judge metrics look like. But look at this mutable genome difference. This is where we started a deterministic component. Data clean start and data clean. These two files are the genome file. This is just to actually copy it over in case if we modify it manually, just to keep the standards there. That's all. That's the only purpose of the starter. However, once the genome has been copied, then you can see that the model has decided to update a lot of the things. From a deterministic output, it maintained the deterministic output, but then beyond the deterministic, it actually started putting non-deterministic mutations. So these all mutations are actually coming from our LLM. And how they define these mutations. In the dataset, we provide hints. In LLM calls, it has skills as well as it got a context. So based on a context, based on a skill, and based on a hint of the schema structure, the LLM can decide how to deal with every individual data inconsistency. In a real life, the project we build in our organization, we have a 99% recall rate, which means out of 100 failed deterministic due to inconsistencies, we are able to recall almost 99% out of them. And that's the power of this particular implementation. So let's go back on a CleanLoop example again. So here we process everything deterministically, and once it has been deterministically processed, you can go into data quality loop and understand what exists. It will tell you all the data that it is existed there. And also there will be one log table that explain what exactly we got and diagnostics. And in diagnostics, we have a perfect understanding here, the proposed event. So when a data has been picked up, did we actually revert it? Did we generated a candidate? How do we work along with the LLMs? And when we go through this, it will give you the perfect understanding of everything that before and after to understand where you need to make tuning, where you need to make changes, where you need to make improvements. This is a very detailed way to actually access instead of just the log being logged manually. Right. So there we go. That's a quite detailed work that we discuss. Here is the row decisions. This is also very important. It pick up the row and then it will tell you from each and every function whether the decision was a deterministic or whether the decision was based on a mutation playbook. If you find a mutation playbook, that means the LLM has decided for us instead of just an algorithm that we provided. And if it is a deterministic, then it's an algorithm that we provided. So all the data which are clean were processed by algorithms, but those data which weren't clean was processed by LLMs. Now, what kind of mutations we can actually process? For example, it has CSV and the POMA is broken. It got a CSV and the rows and the columns been shuffled. It got a CSV and some data is missing and LLM understand where the data get from, etc, etc, etc. You can think of anything. Yes, if we can think of anything, yes, we can implement to fix it. That's the power of this particular implementation. Let me give you a very powerful example that we actually achieved in our own organization. We were sitting on more than 50 data feeds, which were extremely inconsistent. Like almost 50% of data was not able to process. And why? Because it comes from various job market. The job market, we collect the data and then we build the outlook for the Indian economy macro. And that to build the Indian economy macro, we need to collect from 50 sources and more than 2 gigabyte of data every month. Manually fixing that data used to cost us around 200k to 300k a year. It was not economically viable. So we decided to get a paid feed from somewhere else. Since we have implemented this particular process 6 months ago, we have now recall rate up to 99% and we have taken out the complete dependency on manual approach. We also can offboard it from our third-party tools and third-party feeds. Now let me show you how accurate it is. So this particular whole dashboard is actually generated by this software 3.0 data jobs, which come from income system feed, which come from government feed, which come from informal service, and from many other places, which are very much nightmare to put into a structured database. However, the success of this particular project was so powerful because the non-deterministic recalling rate was ready to go up to 99%. And therefore, we even built accuracy beyond the professional data feeds that we could ever subscribe for so large sum of money. That's the power of data engineering 3.0, and that's how you can actually build an AI data engineer that permanently will look for the failures and turn your failures into success. Now let's go back on our presentation and complete the lesson. The posts follow the boundary first and autonomy last structure, where each module introduces a new mechanism that relies on the foundation of the previous one. Lesson 1 and 2 are the bound surface. Lesson 3 and 4 where we control the flow, especially the loop, the structure moving to automation, where we will be using AutoGen as orchestration framework. Lesson 5 and 6 are where we add the pressure and search. The complexity is higher there, which will increase by rising difficulty and comparing multiple decisions, candidate and choices. And lesson 7 where we'll wrap up the whole entire loop, whether it's resilient enough for production environment. Let's understand the whole course in one image. This is a contract for the whole course. Keep the shape in mind for every lesson that follows. The model usually is not the slowest part. The real delay is the human reading the failure and fixing it, deciding the next move, carrying the loop memory forward by hand. Now focus on the center. That's the editable surface. The judge stays fixed and the feedback cycle stays cheap through the repeat itself. The ladder is on the right, which matters because the autonomy is earned, not assumed. The prove the narrow loop works first, then add observability, and then only the wider pressure and the search depth. This is something you can also do as a progressive widening up, especially in the loop process. So you can have 10 steps where slowly it starts with the narrow, keep getting out with a higher confidence fixes. Once that higher confidence fixes are through, and towards the end of it, the funnel go further and make sure it provide the enough pressure to carry out the right set of data with the correct resiliency that we want. So it can allow us to decide what is the error margin we are ready to accept. Now, let's understand. So this engine is a simple process. The bounded surface, lock judge, and repeatable loop. Now let's go back on another important diagram. It's a fuel mutation process. The word and the terminology we inherit from the genome, genetics, the biology. So it's a similar process. However, it is very widely used in this context in artificial intelligence. We borrow a lot of biological terminology in artificial intelligence anyways. This diagram shows the actual mutation process. The agent can mutate the genome but cannot rewrite the judge, then decide whether the changes survive or not. The middle divider matters more than label. It's a safety glass, the boundary. On the right, the genome stays highly editable. This is where the look spent most of its search budget because it's the only editable part. At the bottom, failing output, the contract becomes the repair signal, and the repair signal leaves the arena, heads back to the orchestrator. That's what we say. It's earned. Every label releases some more extra pressure and allow the fixes to be go through. But however, whichever the fixes are not successful still go through as a repair signal, and we keep mutating and mutating the genome as long as it takes. So this mutation process in one word, if I have one sentence, if I have to say, is a fixed referee, isolated mutation surface, and faint root back as a repair signal. These particular examples are linked apart from the repair signal will be in the lesson 2 and 3. You have now the contract. Loop stays bounded, judge stays fixed. AutoGen sits above the mutation surface instead of swallowing it. Next, we will zoom into this genome itself, which will be the next part of the slide. Thank you for watching this. Make sure you like and subscribe so whenever the next part arrives, it straight away comes to your timeline. Thank you. I'll see you in lesson 2.